Welcome back. This is 10th lecture in the series on linear maps. Probably this will be the last lecture on this theme. Let if I could finish what I plan to do. All right. Okay. The- today is essentially the theoretical results. Okay. And BSc students, if okay, at least try to understand the statement of the theorems very well, and it's a typical applications if any. It will be nice to go through the proof if you want to go for higher studies later. Okay, and with that, let us get started. Yeah, see what I want to do is yesterday I proved a theorem. Even while I was proving the theorem, I was in two minds because the complete argument I wanted to give, but then it was similar to arguments you had already seen twice in these 10 lectures. So I was a little hesitant. But then when I viewed back the video record, I thought it may be good to give it again in detail, especially for the benefit of beginning students like BSc students. Okay, let me recall what the theorem is about. So as usual, we have V and W, finite spaces. B is an ordered basis of V and B dash is an ordered basis of W. And I have a linear map F from V to W. And recall the coordinate map given any in V, we write it as summation xi vi 1 to m. Therefore, V goes to V square bracket with respect to B, but we will write it as with respect to this. Okay, this is a coordinate. This stands for the column vector x1 to xm. Similarly, W and W goes to W where this is again with respect to B dash. I will suppress it if the point is clear. Y1 to yn. This actually is W with respect to B dash. These are the coordinate maps. All right. And then we talked about the matrix of F with respect to the basis B dash. Okay. Now the theorem which we proved last time was, let us look at any V in V. Let us look at F of V. This is a coordinate vector in where? It is in R and C. Yeah. And this we wanted to say it is this matrix. This is a matrix of size what? N cross M into matrix of V. This is the coordinate representation of V. If you want, you should write this with respect to, this is with respect to B dash, this is with respect to B dash, this is with respect to B. Okay, but since we are fixing B and B dash, so I don't want to clutter the notation, so I will suppress these suffixes B dash, B dash, B, etc. Okay, this is what you wanted to prove. Let us go through the proof quickly with the detail this time. You will see the proof is exactly similar to what you have seen earlier. Okay, so if I write B equal to summation xi vi I equal to 1 to m, and let A be the matrix of F with respect to B dash, and let F of V equal to summation yj wj j equal to 1 to n. Right? So what are we supposed to prove? This equation is nothing other than this equation. Namely, let's look at y1 to yn. This vector, column vector is A times x1 to xm. Okay, this is what we are supposed to prove. Is that clear? Pause, review, proceed. Okay, we want to prove that. Let us do that. Okay, as we did in the last lecture, let us look at, first notice that let us write A as A1 1, A2 1, and A n1, A12, A22, AN2, and A1M, A2M, and ANM. Okay, right? Okay. So what does this thing stand for? Again, let's recall. F of Vj is nothing other than summation A, Ij, and Wi. This I equal to 1 to n. Okay, these are the things which constitute the jth column. Okay, this is the jth column, and jth column correspond to this. Okay, please remember all these things because we are going to go a little fast. Okay, now what is f of v? F of v is f of summation xi vi. All these things we saw yesterday, xi into f of vi. Okay, right. Now what we want to do is we want to expand f of vi here. Okay, I so let us write it. F of v equal to summation xi f of vi I equal to 1 to n. And what is f of vi? This is going to be x1 into f of v1 plus xm into f of vm. Okay, but that is equal to x1 into what is f of v1? A11 w1 plus A21 w2 plus an1 wn. You understand this? Right. But that is our plus next x2 term. x2 into A1 2 w1 plus A22 w2 plus an2 wn. Yeah, and dot 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 last thing will be xm into A1m w1 plus A2m w2 plus ANM wn. Are you sure you follow this? I'm just writing this. Right. Now what is my goal? F of v, I want to write it as yj wj. You understand? Right. So what I will do, I will rewrite this as count. Let us look at all w1 w1 w1. So I have to collect the coefficients. Now I can write as x11 a11 plus x2 a12 plus xm am1, but I will slightly rewrite because of what I have in mind. This is a11 x1 plus a12 x2 plus a1m xm into w1. Now you understand this? I am writing column y, and the second thing will be a21 x1 plus a22 x2 plus a2m xm into w2. Okay, plus dot 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 plus last term is going to be nth term, that is a n1 x1 plus a n2 x2 plus a nm xm into wn. Yeah, in other words, let's employ a shortened notation. Okay, what is this? The first sum is nothing other than a1j x j equal to 1 to n of w1 plus second one will be a2j xj j equal to 1 to n, the whole thing into w2 plus same thing a nj xj equal to 1 to m 1, yeah, this is 1 to m into wn. You understand this? But notice that I have written this vector f of v as a linear combination of w1 to wn, but we know that it is actually y1 w1 y2 w2 dot dot plus yn wn. Since W1 to Wn is a basis, we conclude therefore Y1 must be uniqueness of the expression shows this must be A1j xj j equal to 1 to m, and yn equal to summation anj xj j equal to 1 to n. In other words, yi is going to be summation aij xj j equal to 1 to n. Okay. Therefore, I have y1 to yn equal to summation a1j xj, summation a2j xj, etc. summation anj xj. Right? This is nothing other than a11, a12, a1m, a21, a22, a2m, and an1, an2, anm multiplied x1, x2, xm. For example, let's look at the first. What is y1? a11 x1 plus a12 x2 plus a1m xm. That's what I got. Yeah. So we have proved the result. Okay. The result is proved. Now you can see why I was hesitant. You see that this way of explicit writing, adding column wise, that is same as saying interchanging the summation notation. Do you understand this? This we had already done many times. What is the first one? This was x. Let me call it. What did I notation I used? Yeah. Okay, let me write it. xi f of vi I equal to 1 to m, but that is summation xi I equal to 1 to m, and j, this we wrote is a is going to be a of j I wj, j equal to 1 to n. This we can rewrite as a j I xi, and then take a summation over. This is what is the summation over? This is over I, this is summation over j into wj. So we got it. You understand? I thought this you by now students will be able to do. That's why I went fast. It's very easy. But okay, please go through, make sure you understand this kind of thing. Do you remember I said how to interchange? I actually said in one of my videos, BSc students have problem with this. So let me write explicitly. You understand? So the same thing is what we are doing here. Okay. So pause, review, and proceed. I hope you should be happy now. Okay. The next result, this is one theoretical result. And remember, this is what we used to prove the following result. LBW2 M of n cross m, or the map F going to this is a linear isomorphism. Okay. As a using the above result, we proved it in the last video, video number 9 on lecture real algebra. Okay. Today what we want to do is a new theorem. Suppose I have three vector spaces, all are pan-dimensional U, V, W. And suppose I have a linear map F and I have a linear map G here. And again, let us look at B1 is an ordered basis for U, B2 is ordered basis for V, and B3 ordered basis for W. Also, let us give a name. This is UI, 1 less than equal to I, less than equal to M, and Bj, 1 less than equal to J, less than equal to N, and Wk, 1 less than equal to K, less than equal to P. So dimension of this is M, this is N, this is P. Right? So now I have a linear map G composed F. From where to where? U to W. What are the bases of my choice here, ordered bases? This is B1 and B3. You understand? Now what is my question? My question is the following. So let us look at G composed F. the matrix representation of this linear map from U to W, and I also have, okay, the matrix representation. Again, notice that, okay, we will write it. So now let's look at the matrix F of B1 to B2. What is this? This is of dimension what? P cross M. This is of dimension N cross M. And let us look at this B2 to B3. Okay, this is a matrix of G. What is its dimension? That's dimension P cross N. You understand? So I want to know there are three matrices, whether there is any relation between them. Notice that this is a composite. Now I have two matrices. One is P cross N, another is N cross M. So it is very tempting to say this. Multiply this matrix F of, okay, I'm writing F. Okay, I don't want to write B1, B2, B2, B3, B1, B3, etc. Right? If our ideas are clear, let us look at this B cross N. This is N cross M. Therefore, I should get P cross M. So I would like to know whether these are equal. Is the question clear? G composite F. This is a P cross M matrix. Whether it is equal to this matrix, which is P cross N, times this matrix, which is N cross M. This is the question. Okay. Pause, review, and proceed. Try to understand. Don't worry about the proof now. Try to understand. Okay, you should have that feeling. Okay, in any subject, you have to develop the intuition also along with the rigor. Okay, and just kind of asking questions and trying to wonder, trying to make a guess, conjecture. This builds up your intuition. Okay, as you go along, you will see your intuition becomes stronger and stronger. Okay, good. Is that clear to all? Okay, it's a child's play. Okay, to prove this is a child's play. Now how? Let us see that. Let us look at simple. Okay, so f of vi, let me write this as a j I f of ui. Sorry, u is our u v w. Here it is u v and w. Right? Yeah, this is vj. This j is going to be 1 to n. This I is going to be 1 less than or equal to m. Right? Now what is g composite f of ui then is what I have to look at. Now again look at what will be g of vj. G of vj, I can write it as b k j into w k k equal to 1 to p. You understood this? Right. Therefore, g of this is g of f of ui. But what is this? F of ui is this, and g is linear. Therefore, I can write it as a j I, j running from 1 to n of f of u, g of f of ui. Is that clear? Okay. But I know what is f of ui. So let me write this. Yeah. But f of ui is summation j. Do you mind if I don't write this 1 to n, etc.? Okay. Beginning students may have problem. Okay. G of this is g of summation a j bj. Right? See this. See, already I made a mistake. This I equal to 1 to n. This is j equal to 1 to m. This is j equal to 1 to n. Are you okay? Right. Now this I can rewrite as summation I equal to 1 to m a j I into summation. This is sorry. Yeah, this is okay. I'm really sorry. I'm making a lot of mistakes. F of ui is this one, therefore f of ui will be summation g into vj. See, I got carried away, so let me start again. Okay, I'm sorry for the goofing. F of ui equal to g of f of ui. What is f of ui? F of ui was over j a j I v j. This is v. J equal to 1 to n. Therefore, this is equal to g of summation j equal to 1 to n a j I v j. Okay, but that's equal to summation over j equal to 1 to n a j I g of v j. Yeah, now we are on correct path. Yeah, but this is summation j equal to 1 to n a j I. What is g of vj? G of vj is bkj wk. Bkj summation over k wk. Right? There is a summation k equal to 1 to p now. You understand this? Let me write it again. J equal to 1 to n a j I summation bkj wk k equal to 1 to p. All right, correct. Now I think you must be an expert in interchanging the sum, right? What do? I write each of those things as a complete, expand this and then add column wise, therefore w1 etc comes. Okay, now I'm not going to do it. Enough is enough. Now you should be, so I can write it as k equal to 1 to p of summation. I can write it as bkj aj and this is okay j running from 1 to n. You understand this? Into wk. Okay, check this if you want by using the above trick, this kind of trick. Okay, so you have to use this kind of trick. Okay, then you can add column wise. We had already seen it earlier. Is that all right? Okay, now what I have done, sorry, g composite f of ui I have written as something like ckwk k equal to 1 to p. Is it okay? What are ck? Because the matrix of g composite f with respect to b1 b3 will be, okay, this will be I, this will be ith column, right? Ith column. Ith column of this will be this one. You understand this? If you want, I should also denote by I. But at present, let me not do that. Are you following me? This I can write as summation cki wk k equal to 1 to p. Then these coefficients form the ith column of this matrix representation. Okay? You follow? Because the whole thing depends on I, so I'm just writing it I here. That's it. So what is the okay? So let us write g comes of ui as summation cki wk. This I can do it. Okay, but I have written g comes of ui already as this. Therefore, what should be my cki? You understand this? Compare this one dagger and compare this star. Okay, these two things, what do they say? This says my cki, okay, is going to be, for a fixed k, it is going to be summation bkj aj and j running from 1 to n. You understand this? Are you sure? But what is this? This is nothing other than, okay, kth entry of the matrix product. This is kth entry of b times a. Yeah, What will be kth entry? bk1, bk2, and bk. Now b has how many columns? Columns will be n, bkn. This is the kth row. And what will be the this one? This is going to be jth. What is the jth one? The ith column of a. Ith column of a is a1i, a2i, a ni. This is the ith column. Do you understand? So when I multiply, what will I get? bk1, a1i, bk2, a2i, bkn, ani. That's exactly this. Right? You understand this? Therefore, the matrix of G composed F is the product of the matrices B times A, where B is B JK. Okay, B is the matrix G with respect to B2, B3, and A is the matrix of F with respect to B1, B2. This is B times A. Please pause, review, proceed. Okay, right. Now let's do. You can do some numerical examples, like something like R2 to R3. Let us say x comma y going to x plus y, x minus y, and 2x plus 3y. And this from this to R2, that will be, let us say, here let us assume the coordinates are u, v, w. These are the coordinates for this. Okay, when you want, okay, let us make it r, s, t. These are the coordinates of R3 to R2. So that may be something like uh, r plus s plus t. Okay, that means this will be x plus y plus x minus y. That is the first, and the next one will be x plus y into 3x. That is 3x plus 4y. You understand? All right. So you can write down with respect to standard base of R2, R3. Again, the same standard base of R2. You can write down the matrix for this map, matrix for this map, and you can write down the matrix directly. Xy go to, where does it go to? It goes to 2x, right? This is 2x plus 3x plus 4y. So you can check whether the maps are correct. Do you want to check me? Do you want to check? If you are a BSc student, you should do that. Okay, what is the matrix of this? Already I said that the matrix of, call this F, call this G with respect to standard basis. I already told you how to write down the matrix. The first column is going to be, look at the coefficients of 1. That is 1, 1, 2. And coefficients of y, that is 1, minus 1, 3. And what is the matrix of G? That is, look at again the same trick. RST, where does it go to? Okay, where does it go to? R, you have to again look at the same way, that goes to 1, yeah, and 0. And where does S go to? That goes to 1 and 1. Where does T go to? 0 and 1. So what you have to do? You have to multiply. So 1 times this, 1 plus 1. Right? Now let us, what is this matrix? G composite of, what is the matrix? XY going to 2x, therefore it should be 2 and 0 and 3 and 4. Okay, I hope you will get it correct. Okay, I see a problem here. RST. Okay, RST, where does it go to? R plus S and S plus T. Very good. Therefore, I have to look at the coefficients of R and write it as a coefficient. That is 1, 0, 0. That will go as 1, 0. That's correct. And S will be 0, 1, 0. That will go as 1, 1. And T will be 0, 0, 0, 1. That will go to 0, 1. I think this is correct. Therefore, this times I have to multiply this 1, 1, 1 minus 1, 2, 3, right? So let us multiply first row by first column, that will be 2. First row by second column will be wait a minute. Okay, let us say first row by first column 1 into 1, 1 into 1, 0 into 2, 0, therefore it is 2. 1 into this is 0, and this will be 0 into 1 into 2, 3, and this will be 0 into minus 1 plus 3, therefore it will be 2. 2 plus 2, 4. Okay, I'm making a mistake. Let us see. What is the matrix of this? Matrix is going to be 2x, therefore 1 will go to 2 comma 0. Okay, and 0 1 will go to, yeah, see, this is where I made the mistake. Sorry, I was in a hurry. So this is 1 0 will go to 2 comma 3. You see that I wrote the mistake wrongly. The coordinates of x will be 2 comma 3. The coordinates of y will be 0 comma 4, right? Yeah, right. Now let's do that. So second row is what I have to look at. Second row by second column will be 0 times 0, 1. 1 times minus 1 will be minus 1. I get a 2 here, whereas I should get a 4. So there is something wrong I have done. So this may be, let us look at that. I think 1 and minus 1 I might have changed. So let us look at what happens to uh, 1, y goes to 1, minus 1 and 3. That seems to be correct. 1, 0, 0, 1, 0, 1. Where does it go to? It goes to 1, minus 1 and 3. 1 minus 1 and 3. This is correct. Okay. And G, where does it go to? It goes to RST goes to R plus S plus T. Therefore, R goes to 1 0 0. That goes to 1 0. Yeah, 1 and 0. And 1 goes to 0 1 0 goes to 1 1. T, that is 0 0 1 goes to 0 1. That's correct. First row, therefore first row by second column will be 1 into 1. Yeah. Second row will be 0 into 0, 1, 1 0, 1 minus 1 plus 1 into 3. That will be 2. That means I have made some mistake here. Let us go through. So here I should have done something s plus t. See, s plus t is x minus y plus 2x plus 3. Therefore, this is 3x plus 2y. See, you see that? Okay. So in a hurry, I made a mistake. This is actually 2. Therefore, it's actually 2. The matrix is 1 minus 1, 2. Are you following? Are you happy with this? This matrix is 2. So they are equal. Okay. This is a product. This is okay. Please check it. Okay. Do not worry about my confusion, because if I do on my own, I will do it correctly. Since I am explaining, I am also in a hurry. I do mistakes. Okay. But I'm sure you can do better than I do it. Okay. Now I have another 20 minutes. This is the most important theorem which you want to look at. Okay. Now what do I have is two vector spaces as usual pan-dimensional. Now I have something else now. I have a basis B1 and B2, two ordered basis for B. And I have two ordered basis for B1 dash and B2 dash. Instead of B and B dash, I'm using B1 dash, B dash. I have a linear map F. Okay. Now, can you, do you know what question I'm going to ask? F is a linear map from B to W. I have two ordered bases B1, B2 on B, B1 dash and B2 dash on W. There is an obvious thing you can ask. What is that? I can form the matrix of B with respect to the ordered basis B1 and B2. I can also may find the matrix of F with respect to the ordered basis B2 and B2 dash. You understand this? So what is the question? What is the relation between them? That is, it is exactly similar to what we did. Do you remember that? For B, if I have B and B dash two ordered bases, then I have a coordinate system B and the coordinate system with respect to B dash, how are they related? It's exactly similar question. Do you appreciate this? Yeah. Okay. Because if you want to learn any kind of science, the questions are more important. Okay. That makes you more creative. You should. Okay. That also gives you intuition. You can ask questions only if you understand the subject well. Is that question clear now? Okay. Pause, review, and proceed. So this is also very similar to the earlier one. So let us start with that. So let us look at B. So let me just, I have to keep it in mind what are the things. So let me write it. I have V and W and I have B1 and B2 here and B1 dash and B2 dash here, right? Therefore, what do we know? B1. So let R be the transition matrix. Okay. What we used to call A B1 dash B1. Sorry. Yeah. B2 B1. Okay. There's transition matrix B2 B1. And yes, be the transition matrix on this one, that is B2 dash to B2 dash to B1 dash. Okay, I may get confused with this, so just to make sure that I am following it properly, B1 and B2. Okay, from B2 to, remember that as I said that earlier, V and B dash, what did we find? We found out that, anyway, I am going to write it. So this we wrote it as the transition matrix. This is the transition matrix A from B to B1. Okay, this is the transition matrix of V into B2. Do you remember that? Similarly, for W, I have B2 is R, not R, no, it is yes. This is a transition matrix B2, right? B2 dash, B2, B2 dash, and B1 dash. Okay, here it is 1 and right. Okay, so this is W B2 dash is equal to B1 dash. No, no, this is always, sorry, this is W of B2 or the original basis, right? Therefore, the same thing. So W of what are the things? W of the original thing is B1 dash equal to W, yes, W B2 dash. Okay. Are you okay? Just because I have to keep track of this, I'm making some mistakes. That's why I wrote. Okay, the dash things must be W. Therefore, the original basis is B1 dash and new basis B2 dash. Therefore, the coordinates with respect to original basis can be written as transition matrix times the coordinates with respect to the second. The same thing here. Is that clear? Okay. Next one is we have this f of v with respect to this is b. This is where this is in W. Therefore, it's a B1 dash with respect to B1. So this we have seen is f of this is B1 dash into V into B1. just to make sure you understand all these things. So this is V of V1 equal to R of V V2. This is 1, this is 2, this is 3. Yes? Okay. Keep your concepts clear. Therefore, even if you make some notational mistake, you can recover. But if you try to remember, you will get confused. Okay, done. You can see that I also made some mistakes with respect to notation, but I recovered. Okay, now what do? I want to substitute in place of W f of B. See, what is my aim now? I want to look at this in terms of, what is it? B2 dash, yeah, B2 dash, and I want to write it in terms of something. Okay, so let me go through. So I want to substitute f of p in place of w in 2. Okay, w equal to f of p in 2. So what do I get? I get f of v b1 dash. That is the coordinate representation of f of v with respect to b1 dash is going to be s into f of v, the coordinate representation with the p2 dash. Sorry. Yeah, you understood this? Right. Now I want to concentrate S f of b b2 dash. So let me write it this way: S of f of b b2 dash equal to f of b b1 dash. Now let's look at what is f of b b1 dash. We know that that is equal to the matrix of f with respect to b1 b1 dash, okay, into the coordinates of this with respect to b1, right? But what do I want? I want the matrix representation of f of b with respect to b2 dash. Therefore, it should be in terms of the other one should also be some accordingly here, right? So with respect to, so I should express this in terms of b2. Okay, don't get confused. So no, this is this coordinate vector with respect to b1. We know it is r times the coordinate vector of v with respect to b2. So I'm substituting that here into b1 b1 dash into r into coordinates of this with respect to b2. You follow that? Now notice that from the last thing we already know this transition matrix are invertible. Okay, we had already known fact. In fact, it also follows from just now what we proved in the about the composition of linear maps, but I'll come to it in a minute. Okay, so if you this we had already seen. Okay, we will give another proof once we complete this. Okay, now look at this. Therefore, I can write f of v b2 dash equal to, I can multiply this by S inverse. S inverse, this is a matrix, and b1 dash into r into v of b2. Okay, have you understood this? Sure. Now what we have shown, remember we have shown that f of v, okay, with respect to whatever it is b dash is f of this with respect to b dash and b, etc. And we have shown this matrix is the unique matrix with this property. If you call this as matrix A, this matrix is unique with respect to this property. Therefore, this tells us the matrix of F, okay, with respect to B, B2 and B2 and B2 dash is S inverse of matrix of F with respect to B1 and B1 dash into R. What are they? They are the transition matrix. This is the transition matrix corresponding to the pair B1, B2. This is the transition matrix corresponding to the pair B1 dash and B2 dash. Okay. Again, you should understand, just as a cross check, let us do one more thing, whether they are agree in thing. Now, what is S? S is a transition matrix where on W, and this dimension is n. Therefore, this, yeah, S inverse will be an n cross n matrix. And what will be F? F is from B to W, therefore it's a n cross m matrix. And what is R? That is an m cross, R is what? Uh, n, this is we can n cross m, and R is the transition matrix on m. Therefore, this is n cross. This is therefore n cross m matrix. That is what it should be, because this is a matrix representation from B to W. Its size should be n cross m. Its type should be n cross m. So at least they tally up. You understand? So let us call M2 as the matrix of F with respect to B2, B2 dash. In fact, I should have made this assumption earlier, this notation, so that life would have been easier for you and me. Okay, this is a matrix with respect to the first basis. This is with respect to the second basis, second pair. Therefore, what I have shown is M2 is S inverse M, M1 and R. And R is a transition matrix from B1 to B2. This is the transition matrix from B1 dash to B2 dash, and hence it's inverse. Therefore, it's actually B2 dash to B1 dash. Okay. So we have found out the relation we wanted. So pause, review, and proceed. Do not lose heart. The, the notation may be slightly more intimidating, but that's why understanding the concepts will make you find the way through the too much of notation. Okay, that's why it took a lot of pain to explain that also. Okay, you can see that even I'm getting trapped, but conceptual understanding helps me to veer around the mistakes. Okay, now let's do two things. Earlier we said the G composed F, whatever the notation, let me not write this, the product of matrices, right? Now let's look at the same thing B, and suppose I have B and B dash, okay, right? Two ordered bases of B. Then let's look at R to be the transition matrix B to B dash, and S to be the transition matrix B dash to B. Okay. Now we had already shown that R composite, yes, R and S are invertible, and R composite of is identity. Why? Start with, okay. So what is my F? F is identity. G is also identity. So what I'm going to go through? I'm going from B to V. Here I have B, and here we have B dash. This is my F. So this is identity. So this is identity with B, B dash. That is your R, right? And this we have seen, this is nothing other than R B dash B. So A B dash B. And similarly, let's look at G V to V, which is identity, but then here B dash to B. And this is again identity, but this is from B dash to B. This we know is transition matrix with respect to B and B dash. We had seen all these things, right? Now, what is G composed of? G composed of is V to V, but the domain basis is V, and codomain basis is also V. Therefore, G composed of is identity with respect to the same basis BB. So we have seen identity matrix with respect to the same basis is the identity matrix, right? But this is a product of G into product of F. That is identity matrix. Therefore, this matrix is invertible, this matrix is invertible. But what is this matrix? This is G. What is this matrix? This is the matrix F. Therefore, they are all invertible. Okay. See, since we have seen many times, I'm going fast. Okay. And usually, what students do is they just learn something, they think they understood and keep. And after that, when similar thing occurs later, they struggle. That is why I keep saying, whatever, once you understand, review it. Second time, it will be easier. You'll have confidence. No, I can do it myself. Okay. Now, the last one. Okay. The last one is this. Suppose I have a linear map F from B to V, the same, right? With respect to this basis, same basis, I'll have a matrix BB, call it A, and with respect to another basis B dash B dash and V, okay? I'll have B dash, okay? Let me call it T. Let me call it C. Since I already used B, let me call it C. All right. Notice that the matrix representations A and C may look different. That's because I chose a basis. But the underlying linear map is the same, right? You understand this? It's like saying I have a 100 rupee note. I can have it 2 times 50 rupee note, or 10 times 10 rupee note, or 5 times 20 rupee note. But the basic amount is same thing, 100. So the matrix A and matrix C may look different, but they denote the same linear map. Okay. So I got A because I worked with some different bases. I got a C for same F because I worked with a different basis. So now what did we find out from the earlier one is that, okay, this these two matrices are related by something like T inverse A T, where T is the transition matrix A B dash B. Okay, because in place of W I am writing B. So this will be an exercise. Please go through it. Okay, right. So this introduces the word called two matrices are called similar. If I can find an invertible matrix T, so that C equal to T inverse AT. Okay, and why do I have to study similar matrices? Because if I think of matrices as linear maps, okay, then the linear map for different matrices may turn out to be the same map. Okay, so the same linear map has two different matrix representation by the choice of my basis. That is why these are all little too abstract, but just to bear with it, go back and try to understand. Okay, it will make your life easy if you go to MSc. Okay, so that ends the thing. Toward the end, that ends all my lectures on linear maps. Towards the end, the notation might have been complicated. If you are a BSc student, you might have struggled with that. Okay, but don't lose heart. Again, try. Okay, you will find that it becomes easy. Okay, and when you go for higher studies, you will actually appreciate. Okay, the teacher will go very fast, but you would have understood very well earlier, so you can cope with it. Okay, so stay focused and learn it well. All the best.